Hi, and welcome to day 28 of Just Start Programming, the Rust programming language. Today, let's continue with Fearless Concurrency. We will revisit shared state concurrency once again, and hopefully, we can finish the next topic, which is extensible concurrency with the send and sync traits. Join me once again, live in one take, no shortcuts and no secrets. Let's just start programming. Right, so here we are. Let's go through once again shared state concurrency. I think yesterday we touched a little bit about mutexes, so let's refresh our memory and then uh, we'll do some of the sample codes here. We'll do some analysis and then we move on to the next topic. Right. So shared state concurrency. There's this slogan from Go language documentation which says, do not communicate by sharing memory. What would communicating by sharing memory look like? In addition, why would message passing enthusiasts caution not to use memory sharing? So there's a difference between the previous approach where you have channels. So in a way, channels in any programming language are similar to single ownership. Single ownership in the sense that once you transfer a value down a channel, you should no longer use that value. In contrast, shared memory concurrency is like multiple ownership. So that becomes even more complicated. Multiple threads can access the same memory location at the same time. So since there are different threads, multiple threads accessing memory location at the same time, then there is a need for some kind of locking mechanism. I think it was mentioned somewhere here. Okay, then we have this using mutexes to allow access to data from one thread at a time. So that approach is using this mutexes. Mutex is an abbreviation for mutual exclusion. As in, mutex allows only one thread to access some data at any given time. To access the data in a mutex, a thread must first signal that it wants access by asking to acquire the mutex lock. Yeah, so here we have this locking concept. The lock is a data structure that is part of the mutex that keeps track who currently has exclusive access to the data. Therefore, the mutex is described as guarding the data it holds by the locking system. So this is the key concept. The mutex is the one guarding the data it holds, and you have the locking system. Mutexes have a reputation for being difficult to use because you have to remember two important rules. You must attempt to acquire the lock before using the data. And when you're done with the data that the mutex guards, you must unlock the data so other threads can acquire lock. I think there's something here where freeing up or unlocking the data is done automatically. Let's see. Where's that? Okay, so this is the metaphor for the concept. Management of mutexes can, yes, management of mutexes can be incredibly tricky to get right. That's why many people are enthusiastic about channels. However, thanks to Rust type system ownership rules, you can't get locking and unlocking wrong. Okay, it's not automatic, but somehow there are some checks in place where it ensures that you get locking and unlocking right and not wrong. Okay, the API of mutex of type T. So this is the example, basic and example, where you have a mutex containing I32 with a value 5, and then you have the variable m, and in here I think not be needed, but it's for illustration to define the scope. Within this scope you have m, lock, and wrap. Okay, so this is the description of this code, or the explanation of this code is over here. To access the data inside the mutex, we use the lock method to acquire. So lock is, it's not to lock access but to acquire the lock. This call will block current threads, so it can't do any work until it's our turn to have the lock. So other threads are not allowed. So in a way, it's still locking others, but unlocking for the one accessing it, which is the current thread. So a call to lock would fail if another thread holding the lock panics. In that case, no one would ever be able to get the lock. That's why we have the unwrap here. After we've acquired the lock, we can treat the return value named num in this case as a mutable reference to the data inside. The type system ensures that we acquire the lock before using the value in M. Num, okay. Mutable reference to the data inside. So mutable reference to the data inside. At this point, it's mutable. I think this one is dereferencing it and setting it to 6. Okay, let's see the explanation. The type of M is mutex I32, not I32. Okay, mutex I. So we must call lock to be able to use I32. As you might suspect, mutex is a smart pointer. More accurately, the call to lock returns a smart pointer called mutex guard, wrapped in a lock result that we handle with a call to unwrap. Lock result, the return of lock result, if it panics, unwrapped is called. Mutex guard smart pointer implements deref to point at our inner data, so dereferencing. The smart pointer also has a drop implementation. Okay, so the implementation of drop releases the lock automatically when a mutex guard goes out of scope. So that's the purpose of having this scope here. So after this, to call the drop, and then mutex guard goes out of scope. Okay. As a result, we don't risk forgetting to release the lock and blocking the mutex from being used by other threads because the lock releases happens automatically. Ah, yes. So somehow I remembered something. That is good. So I hope you remembered that too. Lock releases happens automatically. I think it's due to this drop trait implementation. Yeah. After dropping the lock, we can print the mutex value and see that we were able to change the inner I32 to 6. I32 to 6. Okay. Let's check our code if we have it there. Yeah, so this is what we had yesterday. And here, if you see, lock result, it says that there's a, it returns lock result. Yeah, here, lock result. Which contains mutex guard. Okay, and then unwrap. Okay, unwrap returns a contain OK value consuming self value. Yeah, so this is the error handling. Panics if the value is an error with a panic message provided by error's value. So it's a mutex guard. It's a mutex guard. And then here, mutex guard. So it's a smart pointer. It says it's a smart pointer where we have, I think this one will do the dereference, mutably dereferences the value. So num here is set to 6. And then here we print out m. So it should display 6 at that point. Let's try to run this. Yeah, you can see inside it's 6. So it's printing the mutex. It's printing the mutex because of this pretty formatting. Okay, so that's the basic example. And here, sharing a mutex t between multiple threads. So that approach is only using one thread. Using mutex t, you spin up 10 threads and have them each increment a counter value by 1. So the counter goes from 0 to 10. Example in 16-13 will have a compile error. Okay, why will it have a compilation error? Use that error to learn more about using mutex t and how Rust helps us to use it correctly. Okay, so what do we have here? Counter. Okay, so there's a mutex counter and then mutable vector. Okay, let's copy this part. Comment out this part. Then, so there's a for loop here, and then you have move. Okay, so this is the I think it will be explained here later. We've read this yesterday. Then you have closure. Inside the closure, you have num, counter, lock, because this one is the mutex and wrap num. So num is dereference and it's incrementing the value. Okay, so that's the handle. So there will be multiple threads. There will be a total of 10 threads here. Okay, so let's copy this part. Okay. Let's ignore the error because there will be an error. Then here what we have, handle in handles. So you have vector handles. We are iterating through handles as handle, and then join unwrap. So it waits for all threads to finish. And finally, we print result dereferencing counter lock unwrap. What does it do? This part is the num. Yeah, because it's like this one, the asterisk. Okay, so it will not compile. So let's see, borrow of move value counter. Because here we have a move, so meaning inside this closure, counter was already borrowed. Value moved into closure. No, it was moved, not borrowed. It was moved into closure. Move, of course, because counter has type mutex, which does not implement copy. Consider moving the expression out of the loop, so it's only moved once. Maybe this is not what we wanted to do. So let's see what is written here in the book. Okay, so we did the analysis, create 10 threads over a range of numbers, using this thread spawn, and give all the threads the same closure. One that moves the counter into the thread acquires a lock, calling lock method, and then adds 1 to the value in the mutex. The thread finishes running its closure, num will go out of scope and release the lock so another thread can acquire it. In the main thread, we collect all the join handles. Then, as we did in 16-2, we call join on each handle to make sure all threads finish. At that point, the main thread will acquire the lock and print the result in this program. We hinted that this example wouldn't compile. Now let's find out why. Okay, so I think when we mouse over, we get exactly the same description. Move occurs because counter has type mutex, which does not implement the copy trait. Value move. Okay, we have this value move in the closure. Oh, it looks different. Borrow move a value counter. It's the error. Borrow move value counter. Yeah, it's the same. Okay. The error message states that the counter value was moved in a previous iteration. The loop Rust is telling us that we can't move the ownership of lock counter into multiple threads. Let's fix the compile error with multiple ownership method we discussed in chapter 15. And we do that. Multiple ownership method. Okay. Multiple ownership with multiple threads. Chapter 15, we gave a value to multiple owners by using smart pointer, RCT. Oh, yeah. So we had that vector where uh, different variables points to different vectors. Or where was that? Where's the diagram? Let's visit the diagram, RCT. Yeah, this one. There are two lists that both share ownership. Yeah, so sharing ownership. What did they do here? Instead of box, it should be RC, RCT. Okay, so let's go back. Okay, so here we'll wrap the mutex T in RCT. Yeah, so here RC new, just like in chapter 15, RCT, RCT, RC new. RC new. Okay, RC new, mutex new 0. And then that counter RC clone. Okay, so RC is a reference counter, although you're doing clone, but actually it's not copying it. Yes, it keeps track of who is owning a counter in this case. So that's why we have RC clone here. Let's come back to the code. Counter, so we wrap this, and then here before move is being used. Okay, so in between counter is cloned by this reference counter. But why do we have counter? Okay, counter. Okay, so we are borrowing counter here. Then we are doing an RC clone and redefining it here. So here is actually this one. Okay, and then what other changes do we have? This part here is still the same. Okay, so this time I will not copy and paste. Let me try to test myself and see if I understood the concept here. Okay, so first step, we're going to wrap this into RC. Not that one. Not that one. It should be RC new. RC new. Okay. Okay, so that's for counter, and here counter equals RC clone clone, no, not dot, RC clone, cloning the reference or value of counter, reference value of counter. Okay, and counter here is actually now referencing this one. No, referencing smart pointer. Okay, let's save this. RC. What's wrong with RC? Uses. So we need to import. This is not part of RC. Where's the import or the use stdrc? Okay, it's there. Then there's an issue here. Move cannot be sent between threads safely. How do we resolve this part? Receive sent counter lock. Counter mutex RC clone. Required by bound introduced by this call. What is wrong? Block. So this is the closing block. This wrong? Did I miss anything? Yeah, it's correct. Okay. So this one will not compile yet. That's what they say. Not compile yet. Okay. Let's see. Why it will not compile? Here. Counter handle. Okay. Okay. We compile and get different errors. The compiler is teaching us a lot. Required by a bound introduced by this call that up cannot be sent between threads safely. Okay. There's a lot of error, yes. Here's the important part to focus on. RC mutex cannot be sent between threads safely. The compiler is also telling us the reason why. The trait send is not implemented for RC mutex I32. We'll talk about send in the next section. It's one of the traits that ensures the types we use with threads are meant for use in concurrent situations. Okay, unfortunately, RCT is not safe to share across threads. When RCT manages the reference count, it adds to the count for each call to a clone. Yeah. It adds to the count for each call to a clone. and subtracts from the count when each clone is dropped. But it doesn't use any concurrency primitives to make sure the changes to the count. To make sure the changes to the count can't be interrupted by another thread. This could lead to wrong counts. Oh, subtle bugs that could in turn lead to memory leaks or a value being dropped before we are done with it. What we need is a type that is exactly like RCT but one that makes changes to the reference count. Okay, reference count in a thread safe way. Oh, so meaning we cannot use RCT. It just made us realize that we cannot use RCT. And here, there's another option. Atomic reference counting with ARCT. Okay. Fortunately, ARCT is a type like RCT that is safe to use in concurrent situations. The A stands for atomic. Okay, atomic reference count. Yeah. Meaning it's an atomically reference counted type. Atomics are an additional kind of concurrency primitive that we won't cover in detail here. See the standard library documentation for STD Sync Atomic for more details. At this point, you just need to know that atomics work like primitive types but are safe to share across threads. Okay, so they just want us to realize that ARCT is similar to RCT. I mean the concept with A representing as atomic. And then we just need to know that atomics work like primitive types but are safe to share across threads. That's all we need to know now. You might then wonder why all primitive types aren't atomic and why standard library types aren't implemented to use RT by default. The reason is that thread safety comes with a performance penalty that you only want to pay when you really need to. If you're just performing operations on values with a single thread, your code can run faster if it doesn't have to enforce the guarantees atomics provide. Let's return to our example. RCT and RT and RCT have the same API. So we fix our program by changing use line, the call to new, and the call to clone. So they say it's the same. Okay, let's try to change that. std sync argc. Okay, so it's just to replace RCT with argt. std sync, so we can combine the usage of oops and instead of RC okay, we just put a C. Two. Okay, so compilation is gone. We try to run it now. I saved it. Result 10. I see 10. Okay, so each thread that is spawned, they're incrementing num. Okay, so we only change arc and then it worked. Using arct to wrap the mutex t to be able to share ownership across multiple threads. So we have two things here. One is mutex. So it's for multiple threads, and then you need the reference counter, the atomic approach using arct. Okay, so we got exactly the same result. We did it. We counted from 0 to 10, which may not seem very impressive, but it did teach us a lot about mutex-t and thread safety. You can also use this program structure to do more complicated operations than just incrementing a counter. Using this strategy, you can divide a calculation into independent parts, split those parts across threads, and then use a mutex to have each thread update the final result with its part. Note that if you're doing simple numerical operations, there are types simpler than mutex T types provided by this one, module of the standard library. These types provide safe concurrent atomic access to primitive types. Okay, we chose to use mutex T with a primitive type for this example, so we could concentrate on how mutex T works. What other things can we find here? Module atomic. Oh, so there's atomic bool. Atomic is a signed integer size, unsigned I8 U16. So much information. Okay, so let's just continue from here. Similarities between ref cell and RC and mutex and RT. Okay, what are the similarities? RC, T, and RT, that one we understood. Mutex is for the multiple threads where you have the locking. Ref cell, um, oh, okay, mutex and ref cell, because of it provides interior immutability. Okay, you might have noticed that counter is immutable, but we could get a mutable reference to the value inside it. This means mutex T provides interior mutability, as the cell family does. In the same way, we use ref cell in chapter 15 to allow us to mutate contents inside an RCT. Yeah, so it's ref cell wrapping RCT. We use mutex to mutate contents inside an RT. Okay. Another detail to note is that our Rust can protect you from all kinds of logic errors when you use mutxt. Recall from chapter 15 that RCT came with risk of creating reference cycles where two RCT values refer to each other. Yeah, so there's that cycle causing memory leaks. Similarly, mutxt comes with the risk of, it's the opposite. It's creating deadlocks because of the locking mechanism. Another mutex is locking another mutex. This occurs when operation needs to lock two resources and two threads have each acquired one of the locks, causing them to wait for each other forever. If you are interested in deadlocks, try creating a Rust program that has a deadlock. Then research deadlock mitigation strategies for mutexes in any language and have a go at implementing them in Rust. The standard library API documentation for mutex and mutex guard offers useful information. We'll round out this chapter by talking about send and sync traits and how we can use them with custom types. Mutex. I wanted to come back to ref cell once again, just to review a little bit, because I think this is a very important topic here. Okay, so let's come back to ref cell. Where was that? Smart pointers. No. Yeah, smart pointers here. Interior mutability pattern. Okay, unlike RCT, represents a single ownership over the data it holds. Represents single ownership data over the data it holds. Any given time can have either one mutable reference or any number of immutable, but not both. References must always be valid. Maybe if we go to the code, it might refresh our memory, since really don't want to read everything here. Okay. Mock objects. Okay, mock objects. Where's ref cell? Here, ref cell. Mock messenger. Ref cell. It's wrapping vect string. Okay, the sent messages field is now of type ref cell vec string instead of vec string. The new function will create a new ref cell vec string instance around an empty vector. So ref cell new. For the implementation of the send method, the first parameter is still in immutable borrow self, which matches the trait definition. We call borrow mut on the ref cell. Where was it? Borrow mut. Send messages. Okay. Ref cell. To get a mutable reference to the value inside ref cell, which is the vector. Then we can call push on the mutable reference to the vector to keep track of the messages sent during the test. So it's all about having an immutable reference, immutable borrow of self. Okay, but you want to change the value, so you are making it as a mutable reference. Aromat. Aromat. So push here is to um, messages. Oh yeah, push here is you're inserting it inside the vector. So you're changing the value of the vector. Yeah. Changing in a way that you're inserting or pushing inside messages. So this is how ref cell is being used here. Okay, so it's interior mutability. So that's the key concept that we need to remember. Interior mutability. Okay, so let's continue with this send and sync and see uh, how it works. Extensible concurrency with the send and sync traits. Interestingly, almost every concurrency feature we've talked about so far in this chapter has been part of the standard library, not the language. Okay, your options for handling concurrency are not limited to the language or the standard library. You can write your own concurrency features or use those written by others. However, among the key concurrency concepts that are embedded in the language rather than the standard library are the STD marker traits, send and sync, allowing transference of ownership between threads with send. The send marker trait indicates that ownership of values of the type implementing send can be transferred between threads. Okay, so there's a send marker. We know trait, but what is a marker trait? Or it's a marker that indicates that ownership of values of the type implementing send can be transferred between threads. Values of the type implementing send can be transferred between threads. Almost every Rust type is sent. Almost every Rust type is sent, but there are some exceptions, including RCT. So this cannot implement send because if you cloned an RCT value and tried to transfer ownership of the clone to another thread, both threads might update the reference count at the same time. It's mainly because of this reason. Both threads might update the reference count at the same time. So RCT is implemented for use in single-threaded situations where you don't want to pay the thread safe performance penalty. Okay, so if we look into the code and if we see RCT, it means it's a single-threaded kind of implementation. Okay, therefore, Rust's type system and trait bounds ensure that you can never accidentally send an RCT value across threads unsafely. It's not possible. You'll get compile time error. When we tried to do this in 16-14, we got an error. The trait send is not implemented for RC mutex. Yeah, so that's what it means when we see this. When we switch to RT, which does implement send upon compile, any type composed entirely of send types is automatically marked as send as well. Almost all primitive types are sent. Okay, almost all primitive types are sent, aside from raw pointers, which we'll discuss in chapter 20. There are smart pointers and there are also raw pointers. Raw pointers. But aren't references considered as raw pointers? Let's see. Allowing access from multiple threads with sync. Okay, so this time it's sync. We have sync trait, which is a marker that indicates that it is safe for the type implementing sync to be referenced from multiple threads. So I assume primitive types is also the same. It will have the sync trait. Okay, let's read on. Continue reading. In other words, any type T implements sync if okay, type T reference. An immutable reference to T implements send, meaning the reference can be sent safely to another thread. Similar to send primitives. Okay, primitive types all implement sync, and types composed entirely of types that implement sync are also implement sync. Okay. The smart pointer RCT also doesn't implement sync for the same reasons that it doesn't implement send. The ref cell T type, which we talked about in chapter 15, and the family of related cell types don't implement sync. The implementation of borrow checking that ref cell does at runtime is not thread safe. Okay, so anything about smart pointer we cannot use in multi-threaded application or multi-threading implementation, and they are not thread safe. The smart pointer mutex T implements sync and can be used to share access with multiple threads, as you saw in previous topic. Implementing send and sync manually is unsafe. Okay, because types composed entirely of other types that implements the send and sync traits also automatically implements send and sync. We don't have to implement those traits manually. Oh, so that's what it means. We don't have to implement them manually. As marker traits, they don't even have any methods to implement. They're just useful for enforcing invariants related to concurrency. Manually implementing these traits involves implementing unsafe Rust code. Talk about using unsafe Rust code in chapter 20. For now, the important information is that building new concurrent types not made up of send and sync parts requires careful thought to uphold the safety guarantees. Okay. The Rustonomicon has more information about these guarantees and how to uphold them. Okay, so this is quite advanced. Okay, I understand now why the other approach where you have the channel kind of implementation is preferred. Yeah. For somebody who just got into Rust, I think this one will take some time to really understand and master the concept. Summary. This isn't the last you'll see the concurrency in this book. The next chapter focuses on async programming, and the project in chapter 21 will use concepts in this chapter in a more realistic situation than the smaller examples discussed here. So we need to be more patient until we get to chapter 21. It's the final course before we can implement something really more realistic. Okay. What day is today? It has been 28 days. But let's continue this. I'm sure by the end of I don't know how long it will take us until we finish the book. We should be able to finally do these things. All right. As mentioned earlier, because very little of how Rust handles concurrency is part of the language, many concurrency solutions are implemented as grades. This evolved more quickly than the standard library, so be sure to search online for the current state-of-the-art grades to use in multi-threaded situations. The Rust standard library provides channels for message passing and smart pointer types, such as mutex and RT, that are safe to use in concurrent contexts. The type system and borrow checker ensure that the code using these solutions won't end up with data races or invalid references. Once you get your code to compile, you can rest assured that it will happily run on multiple threads without the kinds of hard to track down bugs common in other languages. Concurrent programming is no longer a concept to be afraid of. Go forth and make your programs concurrent fearlessly. Yeah, so I think by using this approach, at least we can do something. We need to learn more about, it says here, other crates. There are other crates implementing them. So I assume in chapter 17, there it is, sync and await. If we try to search, let's see, Rust multi threading library 3 years ago. Concurrency list of Rust libraries crates. Using multi-threading in libraries. Maybe let's open this one. Let's see what are those crates. Concurrency, parking lot, spin, Ryan, async block, async channel. Let's check. Maybe we'll see something else here. Asynchronous Rust runtime. Synchronous. This is asynchronous. Multi-threading. Async better than multi-threading. So there's this async programming. This is from the book Ryan. This is Ryan RS Ryan Data Parallelism Library for Rust. Data Parallelism Library for Rust, extremely lightweight, makes it easy to convert a sequential computation into a parallel one. Also guarantees data race freedom. Makes it drop dead simple. To convert sequential iterators into parallel ones. Usually, just change your iterator all into par iter, and Ryan does the rest. Some squares. Change this. No data races using Ryan. Sage with WebAssembly. Okay, so this one looks like a promising library. It's something we can look into also. Rust Ryan. Examples. Simplifies writing parallel code. It achieves this by providing parallel iterators that mirror the functionality of standard Rust iterators, but execute operations in parallel across multiple threads. Okay. Data parallelism. Rust cookbook. Okay, so far we have Ryan. Parallel iterators. Let's see. Rust Ryan alternatives. Two years ago. Async standard, and the future is great, which focuses on latency and this is faster alternative. Crossbeam. Tokyo. Okay, so there's async, std, and futures. Oh, futures may have been mentioned here. Okay. Synchronous programming. Async await futures and streams. Sync await. Okay. Let's see if it's a separate grade. First async program. Get await. Get URL. TPRL. Okay, so TPRL. Okay, this is HTML. Okay, so I think this is used where response text, like REST call. URL. Await. Okay, maybe let's do that in another day, tomorrow or the following day. Let's go through these things here, and hopefully we'll see some, yeah, there's some sample explanations and sample programs. Okay, let's do that in another day. So let's end here for now. And before I finally end, let me thank my supporters. Thank you so much.